Now we have rectangular coordinates and polar coordinates that we could use to describe the location of a point in the plane. So clearly we need to figure out how to go from one to the other. What if you started in polar coordinates, but then realized you needed to use rectangular coordinates, or vice versa? There must be some way, some relationship we can write down to turn polar coordinates into rectangular coordinates and vice versa. So let's start out by imagining going from polar coordinates to rectangular coordinates. So let's imagine that we had a polar axis and some point out here whose polar coordinates we know. So r comma theta in polar coordinates. How could we find the rectangular coordinates for this point? Well, before you can determine the rectangular coordinates for a point, you have to decide what your rectangular coordinate system is. And there's a standard agreed upon way to do that, and that is to make the polar axis our positive x-axis. That means our negative x-axis is to the left, our positive y-axis is straight up, our negative y-axis is straight down. And now we can use these rectangular coordinate axes to find the rectangular coordinates for this point. As usual, to find the rectangular coordinates for a point, you just sort of squash the point down onto the x-axis. That gives you the x-coordinate. And you squash the point horizontally onto the y-axis, and that gives you the y-coordinate for that point. But what is the relationship between all of these coordinates, right? This point, r comma theta in polar coordinates, is x comma y in rectangular coordinates, but how could we actually figure out what x and y are? Well, if you look at this diagram, we have a right triangle hiding in here. The length of the hypotenuse here is r. The adjacent side, or the angle theta, is down here in the lower left. The side adjacent to theta, that's the x-coordinate, and the side opposite theta, that's the y-coordinate. So we can just use some right triangle trigonometry, or the most important diagram, to relate all of these quantities. Cosine of theta in this right triangle is, well, it's the adjacent side, which is x, over the hypotenuse, which is r. And sine of theta is the opposite side, which is y, over the adjacent side, over the hypotenuse, which is r. It's a little bit clumsy to have a mix, right? If we're imagining that we know r and theta, and we want to find x and y, it's a little bit clumsy to have our r and theta on opposite sides of these equations. So let's just rearrange things so that polar is on one side and rectangular is on the other. Just move the r to the other side. So x is r times cosine theta, and y is r times sine theta. All right, these two equations let us start with polar coordinates and convert to rectangular coordinates. So let's look at a couple examples. All right, let me keep that in the screen. So for A, we have, these are polar coordinates, 3, 2 pi over 3. So r is 3, and theta is 2 pi over 3. These are polar coordinates. So x is r, which is 3, times cosine of theta, which is 2 pi over 3. 2 pi over 3 is a nice angle. Of course, I chose this example because it is a nice angle. If this weren't a nice angle, you could either use trigonometric identities to come up with the value for cosine, or just punch it into a calculator if there was nothing better you could do. Okay, but this one we know, cosine of 2 pi over 3 is, think about your unit circle for a second, it's minus 1/2. And so the x-coordinate of this point is minus 3 over 2. And the y-coordinate for this point is 3 times sine of 2 pi over 3. And sine of 2 pi over 3 is square root of 3 over 2. And so the y-coordinate of this point is 3 root 3 over 2. Okay. Just to make sure that this makes sense, let's actually plot this point in polar coordinates and see if these look about right. So let's see. In polar coordinates, 2 pi over 3, that's going to be here. And we're going out 3 units, so there. Okay, and then, so in the x direction, negative 3 halves, that's negative 1.5. And yeah, it looks like this could be about 1.5, right? If this distance 1 swung down to the x-axis, it would land about here. So I can believe that this is 1.5 right here, negative 1.5. And then in the y direction, let's see, square root of 3 is something like 1.7, I think, times 3. Call that, I don't know, a little bit more than 3. I'm sorry, 3 times 1.7 is going to be something like 5-ish. Over 2 is maybe 2.5, something like that. And again, I can believe that that's maybe 2.5. So that's 3 square root 3 over 2. At the very least, we're in the right quadrant. If you make some sort of mistake calculating x and y, you'll find that often it just puts you in the completely wrong quadrant. So as long as you keep track of what quadrant you're in, you can actually catch a lot of mistakes. Okay, let's have a look at b. So for b, our r value is negative 5, and our theta value is pi over 6. This is in polar coordinates. So let's convert this to rectangular coordinates. When we figured out the equations to convert from polar to rectangular, it didn't actually make any assumption about r being positive or negative. So the formulas are exactly the same for negative r values as for positive r values. X equals r cosine theta always works, no matter whether r is positive or negative, or even 0. It doesn't matter if theta is positive or negative. This formula works all the time. So negative 5 times cosine of pi over 6. Cosine pi over 6 is root 3 over 2, so minus 5 root 3 over 2. And y is r sine theta. Again, the fact that r is negative doesn't matter. We can still use this formula. So negative 5 times sine of pi over 6. And sine of pi over 6 is a half, so minus 5 halves. Okay, so this means this point in rectangular coordinates should be negative 5 root 3 over 2, comma, negative 5 over 2. That's in rectangular coordinates. And again, just to make sure we're making sense and in the right quadrant, this angle, pi over 6, looks like this. And so with an r value of negative 5, we would back up into the third quadrant. So out here somewhere, with this diagonal being length 5. And it looks like our rectangular coordinates, they're both negative, so we're in the right quadrant, because in the third quadrant, both coordinates are negative. And it looks like the x-coordinate is the bigger of the two, right? Square root 3 is bigger than 1, so this x-coordinate is larger than the y-coordinate. So the relative sizes of x and y are right, at least.